Yes.
Yeah, good evening, everyone. My name is Dohyeon Park from Yonsei University, and I'm honored to present our mission concept LUMOS, which is Lunar Underground Monitoring via Optical Sensing in this UNISEC-Global meeting. So the contents of this presentation is as follows: introduction, mission objectives, concept of operations, space segment, and implementation plan. So in recent years, global interest in lunar exploration has grown rapidly. Missions such as KPLO from CARI or SLIM from JAXA and Artemis program from NASA are accelerating progress in both robotic and future human exploration of the moon. As long-term human activity on the lunar surface becomes increasingly realistic, we propose this MiG-9 mission concept as a step toward preparing for the future. However, establishing a long-term human presence on the moon is extremely challenging due to the radiation, micrometeorites, or extreme day and night temperature variations. One promising solution is lunar lava tubes, large subsurface cavities that offer natural shielding. These may serve as ideal sites for permanent human bases. Another critical issue is lunar communication. The moon's far side has no direct line of sight to Earth, and overall lunar communication suffers from large path loss. Previous relay missions, such as China's Quechao, relied on large satellites, but we aim to demonstrate that CubeSats can also perform lunar relay operations effectively. So our mission, therefore, carries twofold significance. First, scientifically, it focuses on detecting subsurface lunar lava tubes. Technologically, it aims to demonstrate a CubeSat-scale lunar communication relay, showing that small satellites can also support deep space networking. Together, these capabilities directly contribute to the long-term vision of enabling sustainable human activity on the moon. Now, based on this overall direction, I will explain how we defined our specific mission objectives. We focus first on the scientific objective, which is lava tube detection. Previous studies using L diviner thermal data have shown that regions above subsurface lava tubes tend to exhibit a 10 to 15 Kelvin reduction in diurnal temperature amplitude. This signature is detectable through thermal infrared sensing. So in our mission, we do not rely on absolute temperature measurements. Instead, we focus on collecting continuous TIR data to observe how the surface temperature changes throughout the lunar day and night. By analyzing these diurnal variations, we can identify thermal inertia anomalies that indicate the presence of subsurface lava tubes. And our second mission objective is about lunar communication relay. One of the key benefits of a relay system is that it enables lunar surface access on the far side of the moon to communicate with Earth, despite having no direct line of sight. Another important advantage is that when a relay satellite is available, surface access no longer need to carry large or high-performance communication hardware. Instead, they can allocate more of their mass or power and cost budget toward their primary science payloads, which significantly improves mission efficiency. To achieve this demonstration, we plan to collaborate with the Korea Lunar Lander and Rover mission, which is scheduled to launch on KSLV-3 in 2032. Through this collaboration, we expect to secure a practical relay partner on the lunar surface, allowing us to validate the effectiveness of our CubeSat-based communication relay concept. Now, to achieve these mission objectives, I will explain the mission operations we designed for the system. Let me begin with an overview of our mission configuration. We operate two CubeSats, each built on a 12U platform. Both satellites fly in a circular low lunar orbit at an altitude of 100 kilometers with an inclination of 90 degrees. For ground communication, we plan to use the NASA Deep Space Network. And for lava tube detection, our primary payload is the TIR sensor, and we additionally use a CMOS camera as a complementary visible imager. And next, for the relay communication mission, we employ a UHF transceiver together with a UHF antenna. So to carry out the mission, our CubeSats alternate between two modes every orbit. emission mode and transmission mode. In mission mode, we activate both the TIR sensor and the CMOS camera. The TIR sensor collects thermal infrared data, and the CMOS camera provides visual imagery as supplementary data to support our thermal analysis. For the secondary mission, it receives data from the Korea Lunar Lander and rover and forwards that data back to it via UHF, enabling relay communication. And all science and relay data collected in this mode are stored on board for later downlink. Next is transmission mode. In this mode, the CubeSat focuses on sending or collected science data and the relay data received from KLLR to Earth via S-band. It also receives telecommands from Earth and executes them as required. By alternating between these two modes every orbit, the CubeSat can perform continuous science observations while maintaining regular communication with Earth. Now, to support this mission operations, I will explain how we configure the space segment of our CubeSat system. Here is an overview of our space segment configuration. We selected COTS components with proven lunar or cislunar heritage in order to reduce development risk and ensure deep space reliability. For any in-house components, we plan to conduct full environmental testing, which are vibration, thermal vacuum, and radiation tests. The table here summarizes the components used in each subsystem of our spacecraft. It lists the specific manufacturer and model we selected, along with key parameters such as mass and peak power consumption. On the right side, you can see the overall spacecraft configuration of deployed version and a stowed version. Among the many components, I will now focus on the ones that are particularly important for our mission and for operating in the lunar environment. For our primary mission payload, we use a TIR image sensor, specifically the Teledyne Boson Plus, for detecting lava tubes by measuring surface temperature. By continuously tracking how the temperature changes throughout the lunar day, we can identify regions with unusually low thermal inertia, which may indicate subsurface lava tubes. The lunar surface reaches about 390 to 400 Kelvin during daytime, with a radiance peak around 7 to 9 micrometers. Our sensor operates in the 8 to 14 micrometer, which is LWIR band, which aligns with the LLO diviner instrument's validated thermal science channel. This makes it fully capable of capturing the diurnal thermal cycle necessary for analysis. So at a 100-kilometer orbit, the boson provides a ground sampling distance of about 66.7 meters and a swath width of 34 kilometers. As a complementary payload, we also include a visible range CMOS camera, the Zimerasense Triscape 50. This imager provides optical validation of potential lava tube candidate sites, helping us correlate visible features with the thermal data. For our secondary mission payload, Lunar Communication Relay, we use the GomSpace Nanocom AX100 as our UHF transceiver. To support this transceiver, we use an omnidirectional UHF antenna system from IC Space, designed specifically for 12U CubeSats. It provides 0 dBi gain with an omnidirectional radiation pattern, allowing us to maintain communication links even without precise attitude pointing. This is especially important for the relay operations, where the geometry between the CubeSat and the lunar lander can change rapidly. For TT&C subsystem, we use the Rocket Lab Frontier S, which is S-band transponder. Since the moon has no GPS coverage, orbit determination must rely entirely on the ranging techniques. The Frontier S fully supports the two key ranging methods required for deep space navigation, which is turnaround tone ranging and regenerative PN ranging. Another major advantage is that the Frontier S is fully compatible with the NASA Deep Space Network. This ensures that our CubeSat can communicate reliably with DSN throughout the entire mission. For attitude determination control, our spacecraft is equipped with a standard ADCS module that includes reaction wheels, a star tracker, and coulson sensors. However, in the lunar environment, this is not sufficient because the moon's magnetic field is extremely weak. Magnetocores cannot function effectively in lunar orbit. So to compensate for this limitation, we additionally integrate the Baku-Argo Moon propulsion system. So this thrusters provides the extra control authority needed for momentum unloading and attitude controls that magnetocores would normally handle in low Earth orbit. Moreover, the propulsion system plays an important role at the end of the mission. It enables post-mission disposal, allowing the spacecraft to perform a deorbit or impact sequence in compliance with lunar debris mitigation guidelines. So this diagram shows the overall power interface architecture of our CubeSat. All subsystems are properly matched and integrated with the AndroSat EPS-3 module. Next, this diagram shows the data interface architecture of our CubeSat. All subsystem data interfaces are designed to integrate cleanly with the OBC. And lastly, this flow chart summarizes the RF interface of our CubeSat. It shows how different types of data, such as payload data, telemetry, telecommand, and range signals flow through the communication chain. So to ensure that our system design is reliable, we conducted detailed budget analysis. Let me begin with the power budget. We analyzed power consumption for both operational modes, mission mode and transmission mode. After completing one full cycle of both modes, the state of charge increases slightly from 90% to about 92.8%, and the depth of discharge safely decreased to around 75%. Next, we analyzed link budget. The analysis was performed across 4 cases, which are less band uplink and downlink, and UHF relay uplink and downlink. All cases satisfy a link margin greater than 3 dB, which confirms that our communication system reliably supports both direct S-band communication with the Earth and UHF relay communication with the lunar surface assets. Now, I will briefly explain how we plan to design, develop, and operate the mission going forward. We plan to launch the satellite in 2032 aboard the KSLV-3 so that our mission can be carried out in coordination with the Korea Lunar Lander and rover program. Based on this target launch date, we established the overall implementation plan. Yonsei University already has extensive experience developing multiple CubeSats, and our laboratory is equipped with both a clean room and a clean booth. This allows us to perform oral assembly, integration, and most testing activities in-house. For environment tests, we will work with certified national facilities in Korea. Finally, successful execution of this mission will require close collaboration with CASA and CARI, who manage the KSLV-3 and Korea Lunar Lander and rover programs. Yep, so this concludes the presentation from Team LUMOS. Thank you for listening, and I'm happy to take any questions you may have.